Module 3, Metamorphism and Stress in Rocks. Most essential learning competencies are describe changes in mineral components and texture of rocks due to changes in pressure and temperature. Describe how rocks behave under different types of stress, such as compression, pulling apart, and shearing. Learning objectives, you're going to describe metamorphism and stress in rocks, identify and describe the main types of metamorphism, and classify as well as describe the different types of stress of rocks. What is metamorphism? Metamorphism, it is a mineralogical and structural adjustments of solid rocks to physical and chemical conditions differing from those under which the rocks originally formed. Changes produced by surface conditions such as compaction are usually excluded. As rocks are subjected to great heat and pressure, they begin to undergo several changes. Changes in the minerals like folding, bending, and recrystallization of rocks causes changes in minerals' size and shape. Chemical reactions occur between the minerals to form new sets of minerals that are more stable at the pressure and temperature of the environment, and new minerals form as a result of polymorphic phase transformation. The most important agents of metamorphism includes temperature, pressure, and fluids. Number 1, heat. It is the most important agent. And there are two sources of heat: contact metamorphism, which is heat from magma, and an increase in temperature with depth due to the geothermal gradient. Intrusive magmas or deep burial provide heat, which causes metamorphism. Number 2, pressure. Pressure is produced by overlying rocks, or differential pressure is produced by various stresses, especially from plate collisions. It involved primarily with regional metamorphism. 3. Chemically active fluids. It helps transporting elements from one crystal to a new metamorphic crystal, which is mainly water with other volatile components, thus increases the rate of metamorphism. Metamorphic textures. Texture refers to the size, shape, and arrangement of grains within a rock. When we say foliation, it is any planar arrangement of mineral grains or structural features within a rock. It is a parallel alignment of flatty or elongated minerals, and then foliation can form through rotations of these elongated minerals, recrystallizations of minerals in the directions of prepared orientations, and changing the shape of these equidimensional grains into elongated shapes that are usually aligned. And based from the given pictures or example, before metamorphism, the type of rock we have granite, and through the development of foliation due to directed pressure stress by compression, after metamorphism, it is changes into nice type of rocks. And then we have types of foliated textures. We have slatty cleavage, which is closely spaced planar surfaces along which rocks split. And then we have the schistosity. Based from the given example in the picture, we have the platy minerals that are discernible with the unaided eye, and exhibit a planar or layered structure. And then the rocks having this texture are referred to as schist. And then we have here the gneissic texture, which is the segregations of minerals that leads to a distinctive banded appearances. Number 2, non-foliated metamorphic rocks. This kind of metamorphic rocks that lack foliation, and it developed in environments where stress or deformation is minimal, and typically composed of minerals that exhibit equidimensional crystals. So there are certain main groups based on whether or not rocks are foliated. So there's a changing degree of metamorphism that leads to characteristic of rock series. So in foliated rocks, in shale, we have slate, phyllite, schist, and gneiss. In basalt, we have green schist, amphibolite. In basalt again, we have blue schist, and then eglogite. While in non-foliated rocks, we have here the quartzite, the sandstone, the marble, the limestone, and we have here the low-grade metamorphosed basalt, which is the greenstone, and the high-grade metamorphism, which is the granulite. And another non-foliated rocks, we have the hornfels, which is the claystone, and we have the coal, which is the peat. Number 3, we have porphyroblastic texture. It is a relatively large single crystals which form by metamorphic growth in a more fine-grained matrix, as we have seen here in the given picture. So there is the uneven granular texture of rock caused by the presence of a large crystals known as this porphyroblast, and it is formed during recrystallization in the course of metasomatism of solid rock. Thus, these kinds of metamorphic minerals in a rock reflect the changing conditions of pressure and temperature that the rock experienced. This kind of information is important for understanding aspects of plate tectonics and the formation of mountain ranges. Types of metamorphism. As the temperature and or pressure increases in a body of rock, we say that the rock undergoes prograde metamorphism, or that the grade of metamorphism increases. And when we say metamorphic grade, it's a general term for describing the relative temperature and pressure conditions under which metamorphic rocks form. So the low-grade metamorphism takes place at temperatures between about 200 to 320 degrees Celsius, which is relatively low pressure. A high-grade metamorphism takes place at temperature greater than 320 degrees Celsius. It is a relatively high pressure. As grade of metamorphism increases, the hydrous minerals become less hydrous by losing water, and non-hydrous minerals become more common. 1. Contact metamorphism. It occurs typically around intrusive igneous rocks as a result of the temperature increase caused by the intrusion of magma. And of course, this metamorphic rock is formed within the zone of contact metamorphism. 2. Regional metamorphism. It is caused by large geologic processes such as mountain building, and these rocks, when exposed to the surface, show the unbelievable pressure that caused the rocks to be bent and broken by the mountain building process. And this regional metamorphism is usually produces foliated rocks such as gneiss and schist. Burial metamorphism, it occurs when rocks are deeply buried at depths of more than 2,000 meters or 1.24 miles, and it is commonly occurs in sedimentary basins where rocks are buried deeply by overlying sediments. 4. Hydrothermal metamorphism. This metamorphism as a result of exposure to hot fluids passing through a permeable rocks. Most hydrothermal metamorphism takes place at low pressures and relatively low temperature. Number 5. Impact metamorphism is also known as shock metamorphism. It is when an extraterrestrial body such as meteorite or comet impacts with the Earth, or if there is a very large volcanic explosion, ultra-high pressures can be generated in the impacted rock. And also, it can lead to a planar deformation features, high-pressure polymorphs, shatter cones, all of which provide evidence supporting a ball-like impact. Stress, it is a force for a unit area that is placed on a rock. And we have different types of stress. 1. Confining stress. A deeply buried rock is pushed down by the weight of all the material above it. Since the rock cannot move, it cannot deform, and this is known as confining stress. Next, we have tension stress. So the rocks that are pulled apart are under tension. It lengthens or break apart. The tension is a major type of stress at divergent plate boundaries. Next, 3. Compression stress. This squeezes rocks together, causing rocks to fold or fracture. So this is the most common stress at convergent plate boundaries. Next, we have shear stress. When forces are parallel but moving in opposite directions, the stress is called shear. Shear stress is the most common stress at transform plate boundaries. When stress causes a material to change shape, it has undergone strain or deformation. Deformed rocks are common in geologically active areas. A rock's response to stress depends on the rock type, the surrounding temperature and pressure conditions the rock is under, the length of the time the rock is under stress, and the type of stress. Rocks have these 3 possible responses to increasing stress. We have elastic deformation, wherein the rock returns to its original shape when the stress is removed. And we have the plastic deformation, wherein the rock does not return to its original shape when the stress is removed. And fracture, it means the rock breaks. And this are the examples of illustrations of types of stress. So we have compression stress. It takes place when an object is squeezed, which is most common in convergent plate boundaries. Then we have tension stress, which is occurs when the opposite ends of an object are pulled in opposite direction. That is tension, wherein it is most common in divergent plate boundaries. And we have shear stress, wherein it develops when one surface of an object slides relative to other surface, which is in the form of transform plate boundaries. And we have confining stress, wherein it occurs, the pressure occurs when an object feels the same stress on all sides. That is the confining stress. Then we have activity sheet 1.1 for individual activity. How are metamorphic rocks classified? So part A, you're going to write true if the statement is true. If the statement is false, change the underlying term to make the statement true. And part B, you're going to classify each rock listed as foliated or non-foliated. Activity sheet 1.2 guide questions. In what way does tension affect rocks? How does shear differ from compression and tension? Which type of stress would you expect to occur at transform plate boundaries? Explain your answer. And what will happen if the rocks will not experience stress? And how does stress affect the shape and volume of the rocks? Module 4, Continental Drift and Folding and Faulting of Rocks. Most essential learning competencies are: explain how seafloor spreads, describe the structure and evolution of ocean basins, explain how the movement of plates leads to formation of folds, faults, trenches, volcanoes, rift valleys, and mountain ranges, and describe how layers of rocks are formed. Learning objectives: you're going to describe seafloor spreading and movements of plates, identify evidences that supports the major contentions of the seafloor spreading theory, explain how did ocean basins evolve, what are its features, and describe how layers of rocks are formed. What is seafloor spreading? It is a process that occurs at mid-ocean ridges where new oceanic crust is formed through volcanic activity and then gradually moves away from the ridge. Harry Hammond Hess was an American geologist and a United States Navy officer in World War II, who is considered one of the founding fathers of the unifying theory of plate tectonics. Harry has theorized that the ocean floor is at most only a few 100 million years old, significantly younger than the continents. This is how long it takes for a molten rock to ooze up from a volcanically active mid-ocean ridges, spread sideways to create new seafloor and disappear back into the Earth's deep interior at the ocean trenches. This recycling process, later named seafloor spreading, it carries off older sediment and fossils and moves the continents as new ocean crust spreads away from the ridges. The theory of seafloor spreading by Harry Hess in the year 1960, the ocean floors move like conveyor belts, carrying the continents with them. Since the continents are attached to the ocean floor, seafloor spreading could be the force causing the continents to move. Several types of evidence from the oceans supported by his theory of seafloor spreading. evidence from molten material, magnetic stripes, and drilling samples. This evidence also led scientists to look again at Wegener's theory of continental drift. Whereas Wegener suggested that perhaps the rotation of the Earth caused the continents to shift towards and apart from each other, and it doesn't. Today, we now know that the continents rest on massive slabs of rock called tectonic plates. The plates are always moving and interacting in a process called plate tectonics. And Harry Hess' theory of seafloor spreading maintained that new basaltic oceanic crust forms at a mid-oceanic ridge and slowly push away on both sides towards the continents as more new crust is produced. Measurements indicate that the new crust moves away from a ridge at rates from 2 to 10 cm per year. 1. Evidence from ocean material or from molten material. Geologists believe seafloor spreading results from convection in the mantle and lower crust that brings hotter, less dense, and more plastic material up toward the surface. The colder, more dense rock and sediments such as subducted crustal material sinks toward the mantle. Subduction causes contact and friction with the overlying plate, which results in undescending volcanoes and earthquakes. At this mid-ocean ridge system, molten material erupted from the ocean floor, pushing older material out of the way. So the youngest oceanic crust is formed at the crest of a mid-ocean ridge, and the crust becomes progressively older away from the ridge. Thus, the oldest oceanic crust is then subjected and reassimilated in the mantle. Evidence from magnetic stripes. Earth behaves like a giant magnet with the north and south pole. Evidence shows that the Earth's magnetic poles have reversed themselves approximately 780,000 years ago. Scientists discovered that the rock that makes up the ocean floor lies in a pattern of magnetized stripes. The rocks of the ocean floor that contain iron bits. As they cool and harden, the iron lined up in the direction of the Earth's magnetic field. Scientists were able to find parallel stripes on both sides of the mid-ocean ridge. Magnetic stripes are the result of the reversals of the Earth's field and seafloor spreading. New oceanic crust is magnetized as it forms, and then it moves away from the ridge in both directions. Paleomagnetism is the study of the record of the Earth's magnetic field in rocks, sediment, or archaeological materials. Magnetic minerals and rocks can lock in a record of the direction and intensity of the magnetic field when they form. This record provides information on the past behavior of Earth's magnetic field and the past location of tectonic plates. Based from the picture given, the oceanic crust composed of the gray and orange color, and the brown one is the mantle, and we have the molten material. So the orange represent that the rock formed when Earth's magnetic field was normal, and the gray one, the rock formed when Earth's magnetic field was reversed. 3. Evidence from drilling samples. Rock samples from drilling into the ocean floor are the final fruit of seafloor spreading. When we say Glomar Challenger, it is a drilling ship was built in year 1968. And the Glomar Challenger sent pipes 6 kilometers deep in the ocean to drill hole in the ocean floor. And then scientists found out that the youngest rocks were found near mid-ocean ridges, and the oldest rocks were found far away from mid-ocean ridges. Seafloor spreading model. Seafloor spreading, of course, it happens at the bottom of an ocean as tectonic plates move apart. The motivating force for seafloor spreading ridges is tectonic plate pull rather than magma pressure, although there is a typically significant magma activity at spreading ridges. At the mid-Atlantic ridge, material from the upper mantle rises through the faults between the oceanic plates, wherein the magma comes out of the rift valley, and then magma cools to rock and hardens. It forms new crust as the plates move away from each other, and then this new crust then slowly moves away from the ridge. The oceanic crust and continental crust meet at a trench. It is the place where the earthquakes and volcanoes has taken place. Oceanic crust bends down under the continental crust. The gravity pulls rock towards mantle, and the rock melts to mantle. This seafloor spreading helps explain continental drift in plate tectonics. At oceanic trenches, seafloor crust slides down and under continental crust. As we previously explained regarding earlier theories by Alfred Wegener of continental drift, where the continents flowed through the ocean. The modern idea is that the ocean floor itself moves and carries the continent with it as it expands from mid-ocean ridge. Today, it is accepted that the phenomenon is caused by convection in the weak upper mantle or asthenosphere. Movements of plates. They occur due to divergence, convergence, and transverse movement of plates respectively. Convergent, where the plates move into one another; divergent, where plates move apart; and transform, where plates move sideways in relation to each other. And the movement of the Earth's plates also results in the folding and faulting of the Earth's surface due to processes such as compression, tension, and shearing. And in doing so, there's a deformation and rearrangements of the Earth's crust. The rocks that were originally deposited in horizontal layers can subsequently deform by tectonic forces into folds and faults. So folds constitute the twists and bends in rocks. Basic types of folds, we have anticlines. Anticlines are folded rocks that arc upward and dip away from the center of the fold, where the oldest beds are at the core or at the center. Syncline are concave upward folds, or it is a fold that bends downward, causing the youngest rocks are to be at the center and the oldest are on the outside. You can remember the difference by noting that the anticlines form an A shape and the synclines form the bottom of an S shape. 3. Monocline. It is a gently dipping bends or simple bends in horizontal rock layers. Faults. These are planes of detachment resulting when rocks on either side of the displacement slip past one another. Basic types of faults. Normal faults. These are most common at divergent plate boundaries. It occurs in areas undergoing extension or stretching. Reverse faults are exactly the opposite of normal faults. It occurs in areas undergoing compression or known as squeezing. Strike slip faults. These are vertical fractures where the blocks have mostly moved horizontally. This motion is caused by shearing forces, while the oblique slip fault suggests both normal faulting and strike slip faulting. This is caused by a combination of shearing and tension or compressional forces. So we have here an illustration of faults and folds and why they form. We have the type of deformation, the simple model, the type of stress causing deformation, and the stratigraphic superposition. When we say stratigraphy, it is the study of layered sedimentary rocks, wherein the principle of superposition, it is the undisturbed sequence of sedimentary strata or rock layers. So the layers on the bottom are the oldest, and the above them are the younger layers. So we have the type of deformation. We have no deformation at all. We have the simple model here, and we have the normal fault, which is most common at divergent plate boundaries. The type of stress is extensional stress, and its stratigraphic superposition. It is a normal progression of ages. And then we have reverse fault. It is exact opposite of the normal fault, wherein the type of stress is compressional stress, and its stratigraphic superposition is reverse progression of ages. And then we have the thrust faults, which are most commonly seen at convergent plate boundaries, and the type of stress is compressional stress. And then we have strike slip fault, which is the vertical fractures, and the type of stress is lateral shear stress. And then we have here also the anticline, which is the upward folds. The type of stress is compressional, and the syncline, we have the downward folds, which is the type of stress is also compressional stress. Movements of plates. So we have here the illustrations of stages of ocean basin evolutions. When we say oceanic basin, it can be created by the spreading of the seafloor and the movement of tectonic plates. So when we say ocean basins, they are partially bounded by the continents, but they are interconnected, which is why marine scientists refer to a single world ocean. And there are 5 major subdivisions of the world ocean. We have the Pacific Ocean, the Atlantic Ocean, Indian Ocean, Southern Ocean, and Arctic Ocean. So let us go back to the stages of the ocean basin evolutions. We have the motion, the physiography, and the example. When we say physiography, it refers to the physical patterns and processes of the earth. So it aims for us to understand the forces that produced and changes of rocks, oceans, weather, and global patterns. So we have stage A, embryonic. This is the first stage of ocean basin evolution. And this stage, the rift valley is formed while the continent is begin to split. So the motion is uplift, and the physiography is complex system of linear rift valleys on continent, and its example is East African rift valleys. The next, we have the stage B, the juvenile. It is the stage where the movement that appears and happens is the subsidence of the ocean bottom, and it will spread. The subsidence and the spreading will create the division of the continent, and because of the diverge, the seafloor basalt will be created. So the motion is divergence and it's spreading, and the physiography is narrow seas with margin coast, and the example is the Red Sea. Then next we have the stage C, the mature. The broad ocean basins widens, trenches eventually develop, and subduction begins. This is where this spreading happens, as well as known as divergence, same as the juvenile. But the physiography, the ocean basins with continental margins, and its example is Atlantic and Arctic oceans. Then next we have the stage D. This is known as subduction zone. There is a formation of the subductions of the oceans begin to close up, and one of the simplest ways a subduction zone forms is at the edge of a continent, where one tectonic plate is subdued below another plate. So the motion is convergent and it is subduction, and the physiography is island, arcs, and trenches around the basin edge, and the example is Pacific Ocean. And then next we have the stage E, the terminal. This is where the last of the seafloor is eliminated and continents collide, forming a continental mountain chain. The motion is convergent, combination of collision and uplift, and the physiography is narrow, irregular sea with young mountains, and its example is Mediterranean Sea. And next we have here the stage F, the suturing. It is also known as continental collision stage. In this stage, a movement that appears and happens kind of the same with the mature stage, which are the uplift and the convergence. The physiography, young to mature mountain belts, and its example is Himalaya mountains. Evolution of ocean basins. So as we have previously discussed about the different stages of oceanic basin evolution, the ocean basins form initially by the stretching and splitting, rifting of continental crust. So 180 million years ago, the continents were united in a single supercontinent called Pangaea, and the oceans were likely a single body which covered the whole land called Panthalassa, and due to tectonic theory have since moved to their present situation or position. So the Pacific, Atlantic, and Indian Oceans are conventional ocean basins and are bounded by the continental masses or by ocean ridges and currents. At the southern, we have the Antarctic Ocean, and the North Polar region, the nearly circular Arctic Ocean, almost landlocked except between Greenland and Europe, is considered the fifth ocean subdivision. Next, we have layers of rocks, stratified rocks. When we say stratification, it is the layering that occurs in most sedimentary rocks and in those igneous rocks formed on the Earth's surface. And this layered structure formed by the deposition of sedimentary rocks. Changes between strata are interpreted as the result of fluctuations in the intensity and persistence of the depositional agent, such as currents, wind, or waves, or in changes in the source of the sediments. While when we say the unstratified rocks, the structure of these rocks is crystalline or compact granular. They possess a similar kind of structure throughout their whole body. Most of the igneous rocks and some sedimentary rocks come under unstratified rocks. Granite, marble, trap are few examples of these unstratified rocks. So, the stratigraphy and stratifications have already been discussed. So, we have here Danish scientist Nicholas Sterno, who studied the relative position of sedimentary rocks. The slight changes in particle size or composition results in the formations of layers, also called beds, or the rock layering or bedding is the most obvious feature of sedimentary rocks. When we say law of superposition, it was proposed in the late 17th century by, of course, Nicholas Sterno. It states that in a sequence of sedimentary rock layers, the oldest beds are in the bottom unless the layers have been overturned by tectonics. While the law of original horizontality was first proposed again by Danish geological pioneer Nicholas Sterno, this law states that layers of sediment were originally deposited horizontally under the actions of gravity. Any rock layers that are now folded and tilted have since been altered by later outside forces.
During World War II, scientists at sea were using sophisticated echo technology to track submarines when they turned up surprising information about the ocean floor. There they found a stretch of underwater ridges made of continually erupting volcanoes.
The mid-ocean ridges formed when molten rock rises from inside the earth and then pushes the crust apart.
A vast spreading seafloor strong enough to move the continents. Not only is new crust formed at mid-ocean ridges, but it dips back down again into the interior of the Earth.
You put this all together, and what you get is plate tectonics. The idea that the Earth's crust can be broken up into large pieces or plates that consist of both continents and also pieces of oceanic crust moving together over the face of the Earth.
When two plates collide, sometimes one is pushed downward and melts into magma. Eventually, this red-hot material rises to the surface and explodes, creating a volcano. So new crust is born at mid-ocean ridges and destroyed at deep ocean trenches, like a never-ending conveyor belt. And two plates simply nudging each other can cause catastrophic results, like when the San Andreas Fault slipped in 1906. How fast do the plates move? If you live in the US, you're probably standing on the North American plate. In the course of 1 year, the ground under your feet will move about 2 inches. And over long periods of time, that's enough to reshape the Earth, build mountains, trigger earthquakes, and create volcanoes.
Activity Sheet 1.1 for group activity. Make a Venn diagram of faulting and folding of rocks or plates. For the guide questions, what are the importance of folding and faulting? And how are folding and faulting of landforms created? And how does faulting affect human activities? Activity Sheet 1.2 for individual activity. What is the significance of magnetic patterns on the seafloor? How is the process of seafloor spreading explained? How the movement of plates leads to formation of faults, trenches, volcanoes, rift valleys, and mountain ranges, and how layers of rocks or stratified rocks are formed. And this is our references or our